This is the stinky mic.
Is that the stinky mic?
Bob. Bob. What about Bob? This one doesn't work. Why does that? Did you put that one out there, or was that the?
No,
Okay.
I grabbed it off
It was the. I thought it was the math lady. Okay. All right. This one's working. Oh, one more thing. Can you call up the YouTube of the train again? Let's just look at that quick.
Do you know what the name of that specific one is?
Yeah, Amsterdam Rail Fan, Part 1. Looks like this. Okay, go down the. Keep going. No.
That one?
No. Keep going. There it is. Okay, let me pause the podcast. Okay, that dip in the, go ahead, stop it. That dip in the pitch of the train horn is, you're actually, it's a little bit high when it's coming at you, higher than normal, and then it dips down to a little bit lower than normal as after it passes you. So if you were in the freight yard, you'd hear a tone, a pitch, somewhere between the two that you heard on this video. All right, go ahead and switch over to this one. Okay, and so just to reinforce, that's this YouTube video that you can look at. Just type in rail fanning and Amsterdam, New York, and this is part 1, and there's zillions of them. I want to talk to you about how radar guns work. So this is our first notes section. This is actually a version of the graphic that you had for homework last night. And what I've got depicted here is a pair of signals, and I'm styling them as audio, or I styled them as audio signals for the homework, but now I want to think of them as electromagnetic signals picked up by the radar gun. And actually, one of them is sent out by the radar gun. So the black curve in the middle is, we're going to say that it's got a wavelength of about 30 millimeters. And that's the outgoing signal. And then the red signal on top, sorry the color's not very good on the screen, but this red signal up on top is the return signal. And I set this one, I regraphed everything with and this time with the wavelengths specified, in this case 34 millimeters. Okay? And for convenience, I put horizontal dashed lines in here for the equilibrium level of both signals. So this would be an electromagnetic, so this would be like a voltage that the receiver picks up from the return signal, and then the black one would be the voltage, for instance, of the outgoing signal to the transmitter. So it transmits at a certain frequency and a certain wavelength, and then it comes back at a slightly longer wavelength. So make a note, lambda 2, the return signal, is 34 millimeters. Now, take a look. Here's a close-up of those two signals, okay? And this is from the very far left of that image. And you can see that over here on the left side, the two bumps are just about the same location. Now, what we would say is the two waves are in phase or pretty close to being in phase. So you would have constructive interference at that point. All right. Now, a little bit further down the line, you're going to have out of phase. Now, that one, your bump is almost overtaking the dip. All right. So it's almost dip to bump. In other words, destructive. Right. It's out of phase. And you would, that's the fancy phrase. And this one, you would say it's out of phase by just about half a wavelength, lambda over 2. When they're exactly lambda over 2, you get perfect cancellation. All right? And that means your peak and your bump are right at the same point. And when that happens, you get destructive interference. All right? So, here's another bit of information. Here's the outgoing, the middle curve. That's 30 millimeters. Here's the return signal, 34 millimeters. I don't know how you can sketch it, but the blue curve is the sum of the outgoing and the return. So this is what you'd actually hear if it was audio waves. You would hear beats. But the radar gun is not, an ear. It's not an eardrum. But electronically, you would compare. You would add the voltages, the up and down sinusoidal voltages in your circuit. Just like adding two currents together. Add two voltages together, and this is what you'd get. This blue signal, and you can see that it's got beats to it. All right. And for instance, here's the wavelength of the beats down here. Brianna.
You said when the wavelength over 2, you get
Perfect destructive. That means they're exactly out of phase. So when you're in phase, Brianna, your wavelengths are peak to peak. Your waves are peak to peak, trough to trough. But halfway out of phase, you have a peak and a trough, because the peak is halfway across the wave from the trough. So when you're halfway, behind, you're a little positive and a little negative, and they add up to flat water. All right. So here's get rid of these diagrams here. All right. So here's your eyeball. And this is how the cops nab you. Now, I'm going to give you a little bit more instruction about wavelength and frequency and a wave equation here, but I want to emphasize to you that this picture, this is a graph of the spatial distribution. Okay, I've got lambda, mapped out. So if this were a wire, you'd be able to say, okay, the voltage is high at this part of the wire and it's lower at this other point in the wire. If you were actually looking at the electromagnetic wave itself, you would be able to say the same thing. So these beats, now one thing I want to mention to you, and that is these are snapshots in time. The wave itself, each wave train is moving either to the left or to the right. So those beats are moving to the left or to the right. And they move at a specific speed. Now I want to talk to you about the basic wave equation. And in that, show you the relationship between lambda, wavelength, frequency, F, and the wave speed. V is the speed of propagation for a wave. And this is a generic wave equation. So in general, every time you have a wave phenomenon, or a set of wave phenomena, plural, you're going to have some kind of a wave equation to describe the propagation of the waves. So if you were able to track the wave crests or the wave troughs or something like that from point A to point B and use a stopwatch and stuff, they would obey this particular equation or something very close to this. And even scientists that study the surface of the sun and sunspots and the huge magnetic fields up there, and the state of matter up there on the surface of the sun called plasma. Very difficult physics to figure out F equals ma and so forth. But you can find wave equations that resemble this. Wave equations with a ton of calculus and stuff, but it's going to have the same basic structure. A speed, a wavelength, and a frequency. All right, so here's wavelength, here's frequency. All right, so make a note of that. That's the general form. Now, light has its own version of this formula. Here it is. C equals lambda F. All right, so C is the customary symbol for the speed of light. So in Einstein's famous equation, E equals mc squared, C is equal to the speed of light. All right, now, so the top one, V equals lambda F, you would maybe use something like notation like that if you're studying the speed of sound. The speed of sound waves at sea level is about 343 meters per second, all right? 700 something miles per hour. The speed of light in all frames of reference, in a vacuum anyways, so for instance in outer space, but air is close enough to the air that we breathe is close enough to a vacuum that the speed of light travels through air at about this same speed, 300 million meters per second. In scientific notation, C is equal to 3 times 10 to the 8 meters per second. And if you'll recall, I made a description of the speed of light as measuring the fundamental unit of distance, the meter, in the beginning of the e-textbook. Right? So, but most of the time we just round it off to 3 times 10 to the 8 meters per second. Now, why have I got that? Well, if you do a little bit more physics and use the theory of relativity, the actual formula for the velocity of the source that allows the cops to nab speeders is this one. Go ahead and write it down if you like. It's the ratio between the return frequency, the comeback frequency, and the outgoing or the send frequency. So the policeman, there's a little plate on the back of his radar gun, and it says, frequency equals, 1.21 gigahertz or something like that. Okay, and the return frequency is going to be either just a little bit above that if the car is coming toward you, and it's going to be just a little bit below that if the car is moving away from you. So it's going to be a little sharp, a little bit higher pitch, a little bit higher frequency if the car is coming towards you. And you would, it's not something that you can measure, but the radar gun can measure, can pick up that change in frequency. And if the car is moving away from you, it's going to be a little flat, a little bit lower pitch. All right? So this is a fancy looking formula. You're not going to have to calculate anything with it, but I want to show you kind of how it works. And specifically how the speed, V in this formula is the speed of the car. Okay, actually the velocity, because you could put a minus sign in there for moving away from you or moving towards you, depending on what you want. So if V is positive, all right, then the ratio is greater than 1. All right, so, and I'll show you how that works. Okay, so for instance, let's say that the speed of this car, is pretty fast, 150 million meters per second. That's 50% of the speed of light. So V over C is equal to 1/2. 1 plus V over C is 3/2. So the numerator is 3/2. The denominator is 1/2. And that works out to the square root of 3 when you cancel, the factors of 1/2. And that's a positive 1.73. Now that's a big ratio of return to outgoing. You guys in your vehicles, it's going to be 1.00 and a bunch of zeros, and then a 1 or a 2 or a 3 or something like that. But from that, even a small number greater than 1, they can figure out, they can solve for V. Now, we're not going to solve for V, but some of you can maybe tackle this and solve for V. It's not that hard. You square both sides and you do a little bit of algebra. You get V by itself in terms of the ratio of the frequencies, and then you can just plug that in. And the policeman's radar gun has a little onboard computer, so if he measures a return signal that's slightly higher in frequency, he's going to catch those beats, just like we did on that 3 or 4 slides ago. All right? And if the car is moving away, then the return frequency is going to be slightly lower. He's going to get beats. And that difference in the frequency, the onboard computer on his radar gun, cranks out goes through the Doppler formula that you just saw, that big square root sign, and he gets the speed, and it displays the speed of the car. Whether it's coming towards you or whether it's going away from you, it doesn't matter. All right, so that's how the policeman takes advantage of beats in order to measure the speed of anybody. Baseball, if you ever watch a Major League Baseball game on television, they have somebody with a radar gun, I guess, right behind the batter's box with a radar gun that catches the speed of the baseball, and sometimes they can be, going 100 miles an hour for somebody that's got a real good heater. But anyways, that's how they do it. Let me pause for questions. Okay. Let's talk some more about this stuff from page 130. Last time we demonstrated standing waves. Darian and Caroline did that. They did a nice job with it. And we did the fundamental mode, which I've got, this is a sketch from another website. And then I've got the first excited state and the second excited state and so on. Those are also known as harmonics here. And as I mentioned in the homework to read about that terminology about page 130 and so forth. So instead of calling it the fundamental, some people would call it the first harmonic, and then the second harmonic, and the third harmonic. So for instance, if you're an acoustic engineer and you're analyzing the sound of one of the strings of this guitar, right? You'll find usually that the first harmonic or the fundamental mode is the one that is loudest, okay? But the nature of the sound, a guitar playing a G is going to sound different from a piano hitting the same note. And that's going to sound different from a flute hitting the same note. And the flute is not a string that's vibrating. It's an air column. It's pressure waves that are varying through the length of the flute. And that's going to sound different from, let's see, what other kind of instruments are there? Like a trumpet playing the same note. They're all going to have different mixtures of harmonics. Most of them are going to have the loudest harmonic being the fundamental or the first harmonic. But they'll have mixtures of all of them. Unless you're working with a synthesizer. Now, a synthesizer is an electronic music machine. You choose the tone, and it generates, or it can generate that exact tone. Now, if you press a button on the synthesizer, to make the synthesizer sound like a piano, it'll generate the fundamental and a bunch of other of the higher harmonics in just the right mix to make it sound like a piano, versus an organ, versus a violin. My son's got a little, I don't know, a Sony or a Panasonic or something keyboard, and it's got, you press different buttons, you can get different instruments and stuff, and it's just different mixes of these harmonics. Now, in quantum physics, and this is more the terminology that I've been using, you refer to either the fundamental mode or the ground state. Okay, and that's I'm not an acoustic engineer, so I use this set of terms over here. But it's good to remember both sets of vocabulary terms. All right. So harmonics versus excited states or ground state. Ground state is we're going to, when we get to talking about atoms and electrons in orbit around atoms, we're going to talk about the ground state and then the first excited state and so on. Questions about this before I continue? Okay, let's keep going. I want to talk about the intensity of sound. All right, so we're going to, talk about sound waves again. And so I'm reborrowing this picture. Let's focus on this. And this is beats. So we'll think of this now as an audible, like the tuning forks demonstration that we did in lecture last week. And we heard those beats. And so we know that, the beats correspond to loud where the amplitude is big, and faint where the amplitude is small. So kind of draw some pulses like that, some beats, and where the amplitude, and here's the wavelength of the beats, okay? And where the amplitude is small, in other words, where I have it marked down faint, small amplitude, that's pretty close to flat water, okay? In my graph, it's not perfectly flat, but it's pretty close. And same over here at loud, largest amplitude. If these were ocean waves, this would be the biggest of the rogue waves. All right. So let's think about this, but not as a water wave, not as an electromagnetic wave, but as a sound wave. And what I want to talk about is the decibel scale. All right, and that's table 7.4. Now this is just kind of a listing, and usually I tell you guys don't memorize stuff, but you could memorize a couple of these as good indicators. And on exam 3, I'll probably have a list like this, something like this, on the cover page. The human threshold of hearing is at approximately, they've measured 10 to the minus 12 watts per square meter. Now let me remind you, if I haven't already mentioned it to you, a watt is the same as 1 joule per second. So every square meter of eardrum area that you have, not that anybody has an eardrum that big, but I mean, for every square meter of eardrum area, you have a certain number of watts crossing it, okay? If the sound is just at the 0 decibel level, the threshold of human hearing. Okay, so it's 1 times 10 to the minus 12. A whisper, 20 decibels. You guys heard me because I just whispered, but I have a microphone. I want you to whisper. What is your name again? McGraw? McGuire? I want you to whisper something to McGuire Did you hear? Okay, a few more decibels.
Can you hear what I'm saying?
That's not a whisper, though. See, so, but if you're, whisper something to me. What? She just, no, I don't, no, don't say something to you. Whisper. Anyway, she just said something to you. She took me literally. Typical music major. Okay, anyways, so whisper 20 decibels is pretty low, and notice you guys in the third column over here, the third row, whispering 20 decibels in the middle column, and 1 times 10 to the minus 10 watts per square meter. So every 10 decibels that you add to the decibel rating, that's another power of 10. Right? So you've gone up by 20 between threshold of human hearing, barely audible, 0 decibels, up to 20 decibels whisper, that's another 10 to the 2. So 10 to the minus 12 times 10 to the minus 2, or 10 to the 2 is 10 to the minus 10. And it just keeps going up like that. So library, typical library, 40 decibels. City traffic, 70. Subway train, 90. Hard rock music, 110. Rocket blast off, 180. That's 6 watts per square meter. Oh my goodness. And that's why everybody clears out. You know, when NASA is launching a rocket, or the Air Force out at Cape Canaveral Air Station, they launch one of these rockets, they clear the place out, because you can totally fry your eardrums if you're up close. Same thing with jets taking off. You know, if you're on an aircraft carrier or at the airport, you've seen those guys down there by the plane, they got to wear those super heavy duty earmuffs to protect their hearing. And even then, it's pretty loud. So anyway, so the decibel scales, I'll ask you a couple questions about this, Devin, in the next homework. So just make a note, it's table 7.4, and read that section of the chapter as well. Okay, we're heading for the periodic table. We're going to start talking about electrons and atoms. And I'd like you to write down this web address, webelements.com. It is an online chemistry site that's, I guess it has some advertising in it, so it's not like a nonprofit website. But it's a really, really nice clickable periodic table. And if you click on any element, it'll load up a page about that element. You can look up all its properties, its density, its boiling point, its melting point, all kinds of stuff. The structure of its nucleus, all kinds of jazz for each of the elements in the periodic table. And the periodic table is important for us because each cell of the periodic table encodes the basic atomic structure. So here's a little cell that I magnified for carbon. The symbol is C. The top number is the atomic number, 6. And the number at the bottom, 12.011, that's the atomic mass, or the atomic weight. And the arrangement of cells in the periodic table is meant to also encode physical bulk properties. And it's not implicit. So you don't actually see, the melting points listed in the periodic table, not usually. But everything that happens in stacks and in rows of the periodic table contain a certain specific set of physical properties. So so the cell itself tells you one of the pluribuses, but the unum from E pluribus unum is something like the melting point or the density or any of the other bulk properties of carbon. And so you just look it up. And then if you go to the webelements.com website, you're going to see, you click on the cell for carbon, you'll see all kinds of physical properties of carbon. And that is why the periodic table is important. Because stacks and rows of the periodic table have common patterns of properties. Right? It's not just accidental. The structure of the periodic table encodes an enormous amount of information, starting with the atomic number and the atomic mass. All right, so that's what we're looking at. We want to get to the periodic table as quickly as we can. Let's talk about electrons and the concepts of electricity. The idea of electricity is something that people have noticed since the days of the ancient Greeks and stuff like that. And the word electron comes from the Greek word for amber, A-M-B-E-R. Amber is fossilized pitch from certain kinds of pine trees. And if you rub it on your shirt or on a cloth, it'll pick up little tiny pieces of paper or papyrus if you're in Egypt, or it'll pick up little threads, from your toga, or whatever kind of, or even, if you pull a hair out of your head, it'll probably pick up a little strands of hair if your hair's not too greasy and stuff. So if you don't use conditioner and stuff, you know what? Should we do the Van de Graaff generator next week?
Yeah.
With the hair that flies. All right. A public service announcement. We're going to do the Van de Graaff generator next week on Tuesday. All right. Now, the Van de Graaff generator, you may have seen videos of it on YouTube or on Discovery Channel. It's this generator, electrical generator, and the top of it is like this metallic sphere. And if you put your hands on it and then stand on an insulated mat or an insulated stool, the charge accumulates and it goes from your hands and it'll go to your other extremities like your hair, and it'll make your hair stand on that. Okay? Now, every semester, we try to do that demonstration, and if the air is not too humid, it will actually work fairly well. So we'll try to do it on Tuesday. So if you want to be a student volunteer, and we'll take pictures of you, okay? A student volunteer, and you want to see your hair fly out into the universe, from the Van de Graaff machine, Aaron, and anyone else, just come wash your hair on Monday night or Tuesday morning, but do not put conditioner or any kind of goop in it. We want your hair to be really dry. The drier it is, and the more, like my hair is too short, to show anything. But like Darian's hair would be great, especially if your hair, like my hair is pretty thick, but if you have really fine, thin hair strands, you might do really, really good. So anyways, if you feel like volunteering, and at the beginning of class on Tuesday, just come up and don't wear any earrings, don't wear any metal, the upper part of your body, and we'll try to do that with you if you dare. Anyway, so the mystery of static cling from the days of the ancient Greeks, amber, electron. Electric comes from the Greek word for amber. You observe it every day when you're doing your laundry, unless you put in, a sheet of, what do they call that stuff? Bounce, fabric softener, cling free. Your socks will stick together if you don't do that. All right. And that's what we're talking about. Now, the guy that figured out electrons per se, the objects that actually carry electric charge, his name was J.J. Thompson in England at the end of the 19th century. So 1899, around in there, 1900, he was kind of working on this. And this is a picture of him in his lab. And that device down there is a clear, that's a diagram of a clear glass tube that he designed and had someone make that will allow him to figure out whether this mysterious thing that they had noticed called beta rays were actually positive or negatively charged. In the late 1800s, they'd found that certain elements emitted rays that could expose film and and actually cause electrical effects. One of them was called alpha ray, another one was called beta ray, and the third one was called X-ray. Now, X-ray is what we still refer to as X-rays. Beta rays, he was able to show that a beta ray, it's not really a ray, it's a particle, and it's a charged particle. So here's what he did. He designed a machine that generated beta rays, and then he accelerated them through the beginning of his device and sent them between a positive and a negative plate. So he had two metal plates, and he hooked up one end to the positive end of a battery and the other plate to the negative end of a battery. And he said, all right, let's see what happens when I beam this mysterious beta ray in between the two plates. If it's charged, the beta rays will either swing upwards or swing downwards. You know, if the beta ray is negative, it'll swing upwards toward the positive. If the beta ray is actually a negative particle, if the beta ray is actually a positive particle, it'll swing down away from the positive toward the negative. So he put it inside this glass tube, so he evacuated all the air, sucked, so there's a vacuum. But on the inside of the tube, they painted a little bit of phosphorescent paint, so that if the beta rays hit that, it would glow green. Now, if you've ever seen in a movie, or maybe when you were a little shrimpy kid, a television monitor for a computer or a regular TV that was, not a flat screen like this, but it had a really deep tube. It's called a Cathode Ray Tube, that's the front of that, the glass front of that, had to be painted with phosphorescent paint. And you sometimes still see people with green screen monitors. And those are just cheap glass monitors painted with green phosphorescent paint on the inside. And they steer the electrons at just the right place and time so that, you get letters and figures and things like that on the computer screen. Now, that's in the olden days. But it's the same process. So here's what J.J. Thompson found. He found that the stream of beta rays, go ahead and draw a curved path away from equilibrium up towards the positive plate. And it hit above there, and that upper part of the detection tube glowed green. And when he saw that, he said, aha, this is a particle, and it is a negative particle because it's swinging, it's being deflected upward towards the positive plate as a negative, because opposites attract, so a positive attracts a negative and so forth. Right, now, let's take a look at the basic state of play. So this is a side note about electrons. The unit of charge in the metric system is called the Coulomb, and that is equivalent to the charge of 6.24 times 10 to the 8 protons. And a proton has the same charge as the electron. But the proton is positive, P-R-O, positive, pro, and the electron is negative. All right. So the minus 1 Coulomb corresponds to the charge of the same number of electrons. So if you have 6.24 times 10 to the 18 protons, the charge on each of them is really, really small. But a Coulomb is a household size unit of charge. And so in the metric system, that's the unit of charge. It corresponds to a big, big pile of electrons. And if you're doing some home wiring, or if you're trying to replace the circuit breakers at your house or in your car, a lot of times you'll have to get a circuit breaker with a certain amp rating, like 20 amps. Or if you're in a car, half an amp, 0.5 amps. Amp, that means ampere. An ampere, and this is not in the side note, but you can write this down. The ampere is equal to 1 Coulomb per second of electrons going down the wire past a certain point. Okay, 1 Coulomb per second is an ampere. And so if you have a 20 amp circuit breaker, that means that if you send 20 amps, 20 coulombs per second through that breaker, it's good. But more than that, the breaker will trip. If it's a fuse, the fuse will break. It'll burn up and break the circuit and protect your equipment. All right? So that's what... now, the other way to look at it is the electron charge itself. It's called the fundamental charge, and the symbol is E. It's the smallest that we've found in nature. And it is the quantity of charge on the electron. So over here, the number of charges in a Coulomb is basically this number times 10 to the 24. All right. Another way to write it is that the fundamental charge E is 1.60 times 10 to the minus 19 Coulomb, and actually that should be Coulomb per proton, because there's no negative signs here. All right, so that should be protons. 6.24 times 10 to the 18 protons, and then in the second line down here of this second equation block, that should be coulombs per proton. I've never noticed that before. I'm going to have to go in and change that. Anyway, so the electron, so my lesson to you concerning electrons and stuff and coulombs is simply this, that the fundamental charge of nature, the charge on the proton, the charge on the electron, is incredibly small compared to human scale amounts of charge. A human scale amount of charge is a Coulomb. Coulomb per second is an amp. An amp is a household size current. Okay? The currents flowing around an atom are so much smaller than that, because the currents flowing around an atom are related to what electrons are doing, and they're very, very small. Okay? So 1.602 times 10 to the minus 19 coulombs, 1.602 times 10 to the minus 19 household units in the metric system is equal to the amount of charge on a proton or an electron. So it's very, very small. And that tells you something important about the electron and about us. We're these humans, and we're pretty small in terms of the Earth itself. The Earth is teeny compared to the sun. The sun is teeny compared to other stars like Betelgeuse. And Betelgeuse is pretty small compared to the Milky Way galaxy. The Milky Way galaxy is pretty small compared to the visible universe that we've been able to see so far. But the electron is way, way smaller than us. And so we're made, when we talk about the number of atoms in a glass of water, or the number of atoms inside your left earlobe, or any other, any human-sized object, many, 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 many zillions. I don't even know what 10 to the 18, 10 to the 18, let's figure what that is. 10 to the 18. Okay, that's 10 to the 18th power. 10 to the third power is 1,000. 6th power, million. Ninth power, billion. 12th power, trillion. 15th power, quadrillion. 18th power, quintillion. So there are 6.24 quintillion electrons moving through your household wire per second if it's moving 1 ampere of current. That's a huge number. The number of electrons in your body is even bigger than that. It's even bigger. 1 quintillion, 10 to the 18 electrons is a small number compared to how many there are in your body. So it's kind of amazing when you think about it. All right, let's get back from the side note. Here's what we know is a little summary about what we know about electrons and stuff. We think that the nucleus, for instance, this is a helium nucleus, 2 protons and 2 neutrons, and that there are 2 electrons orbiting the nucleus. Now, I've got the nucleus of the helium kind of in a unsymmetric shaped bag, and actually the vocabulary term bag is actually something that they use to model the physics. It's a word that they use when they're trying to figure out how the nucleus stays together and stuff. So I always like to make it a kind of an uneven, wobbly looking bag of containment for the nucleus. And then the 2 little blue electrons zipping around outside of it. And that's encoded in this tile, this cell, from the periodic table for helium. This is in the upper right of the periodic table. Helium, the name of it, and then the number 2, that's the atomic number. And that stands for 2 protons in the nucleus, 2 electrons in orbit for a neutral helium atom. Total mass of about 4.003. That means that there's, in most helium atoms in the universe, there's about 4 objects, 2 protons and 2 neutrons. By the way, students, a neutron and a proton are about the same mass. They're pretty tiny, but they're about the same. Neutron's a little bit heavier. The electron is tiny in kilograms. So make a note, this second side note, the mass of the electron is about 1/2000th of the mass of proton or neutron, right? So the mass of the electrons doesn't really show up. It doesn't really change this number here, 4.003, because they're pretty small in atomic units, atomic mass. Dare, this thing is logging off. The electron is 1/2000th of the mass, approximately, of proton or neutron. So the neutron and the proton are like almost the same. And divide that mass by 2,000, that gets you about to the right mass of an electron. Now, let's talk about how you charge things up. You know that if you're combing your hair, you can develop static charge in the comb. Or if you take a balloon and rub it in your hair, or balloon and rub it on your shirt, it'll, like stick to your shirt, or it'll stick to your head. Or you can put it on the wall, it'll stick to the wall. And that is because friction basically strips electrons from one substance, and then they're caught by the other substance. They tend to stay on the surface of the other substance. So, for instance, for this girl combing her hair, the comb tends to accumulate a few extra electrons. Electrons are negatory. Therefore, each strand of hair tends to be slightly positive. And it's positive because the electrons are missing. Right? And that's what combing does. It tends to strip electrons from your hair, and then those electrons end up sticking to the comb, right? Unless it's a comb made out of metal, right? But if it's a comb made out of plastic or something like that, that's what's going to happen. Now, you can charge something up by placing it in contact with another charged object that's already charged up. Okay, so you comb your hair and you touch the comb to something else that's not charged, and the other thing will acquire a little bit of negative charge by contact. Right? And there's other methods like polarization. Now, I'm going to show you how polarization works. So make a note of that vocabulary word and underline it, polarization. All right? And here's kind of how it works. If you have that comb, you know, you've combed your hair, it's negative, and then you take, for instance, a piece of paper, you can pick up a little tiny piece of paper because the electrons in the paper try to get away from the electrons, the extra electrons on the comb. The comb is negative, so it has a few extra electrons on it. Okay? The paper is neutral, so it has the same number of protons and electrons, but the electrons are easy to move. They're small. So the electrons will try to back away from the comb. That means closer to the comb, you've got some positive charges where there used to be a perfect mix of positive and negative. Now, the negatives are backed away. The positives are still there. The protons don't really move because they're pretty heavy. All right? And so you're left with something where the near side of the... Go ahead and sketch that paper. It's a piece of a rectangular strip of paper. The near side of it is going to tend to be a little more positive than usual. And the far side of it, far away from the comb, is going to tend to be negative. And that's polarization. You've polarized the material, you've given a direction from a positive side to a negative side. So from positive to negative would be downward. All right? So you've whereas without that comb nearby, it'll just be all, you know, it won't have a net charge, it won't have any polarization. There'll be as many positives in the top half as there are in the bottom half, as many negatives in the top half as there are in the bottom half, and it won't be polarized. Now, I want to show you a cool demonstration, a cool experiment that you can do at home, and I've done this any number of times. Okay, what you do is you take the water in your kitchen sink or the bathroom, and you turn it on just so that it's a stream of water, right? So you don't want droplets per se. You want the thinnest stream of water you can manage, okay? And then take a comb and charge it up, you know, like bring it through your hair or, you know, rub it along your shirt. And actually anything will work, any kind of piece of plastic, but, you know, people use combs for it. And what happens is if you bring the comb next to the stream of water, if the stream of water is thin enough, you'll see it kind of dip to the side, just like this photo. This is an actual photo. If you go home tonight or this afternoon after lunch, you're washing up the dishes, and you take your comb out after you wash the dishes, just have a little teeny stream of water. Yeah, you can do it. Anybody in here can do it. Even if you're the biggest klutz. I'm not looking at anybody. But if you happen to be a klutz, even you can do this. Okay, because there's a net pull force. Okay, and it's a pull force between positive and negatives. All right, so it's a bunch of little pull force arrows right here. Now, here's kind of a picture on a molecular level of what's happening. Right, the water molecule. Go ahead and draw yourself a picture of an H2O molecule. It forms kind of a V. There's two H's, two hydrogens, H2, And then the O, the oxygen, is kind of the middle of the V. And the V is a little bit wider than 90 degrees, right? And I always like to draw an arrow from the hydrogen end of the V towards the back end of the oxygen. And the reason I like to do that is the following. The two hydrogens are very simple. A proton and an electron, all right? The bond between hydrogen and oxygen, there's two of them. It will be because of the electron. In the hydrogen's electron will be getting shared with the oxygen, all right? Now that extra electron is going to be somewhere over here towards the oxygen. And what that means is the hydrogen's proton is going to be way out here. Now, can you dim the lights down to 0 for just a second? I want you to look at the colors of this. Boy, it's still not very good. This one's better, this projector. You can see it's a little redder. The far end of the hydrogen is red. And for me, my code is red positive, blue negative. Right? So that's the end of the molecule, the H end of the molecule. There's going to be a proton out there. And then somewhere between that proton and the oxygen is going to be the hydrogen's electron. It's only got one. And so it's going to be sucked in towards the oxygen. That's how they bond, right? So that electron and then the other one down here in, between this hydrogen and oxygen, those two extra electrons are going to try to, they're going to have a repulsive force on oxygen's original electrons. Oxygen has 8 regular electrons. And those 8 are going to be a little shy. They're going to repel away from the 2 electrons here, somewhere along these dashed lines, the 2 electrons from hydrogen. Right? So the net result is that this end of the oxygen, the V end of the oxygen, is going to tend to have a few extra electrons than normal. The water molecule has been polarized. And then the other end, the hydrogen end, over here and then down over here, those are going to tend to be more positive because there's mainly a proton out there, right? So as a result, if you have a negatively charged Coulomb, look what happens. Dun, 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 dun. It reorients the water molecule, and then what happens? Dun, 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 dun. You get a net pull force. Go ahead and turn to presentation mode. All right, now I have a clicker question for you. Multiple choice. True or false? If true, which true? If false, which false? Think. There's a net pull force here on the water. But does the water exert a pull force on the Coulomb? "15 seconds. Make your decision. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good. Go ahead and show this. The correct answer is A, and it's clear here that there's most of you, let's see, what is it? 54%. The majority of you voted for A. That's good. But a good number of you sprinkled in answers. Who voted for E? You know, I can figure it out. Who voted for E? I'm going to do that. I knew I shouldn't have put that in there. Anyway, go back to the regular one. So let's talk about it. There's your answer. Newton's third law still holds. This is an electromagnetic interaction. Nothing's... No. Now let me ask you another one. Clicker question number 2. Why is the net force a pull to the right? Now this one I want you to think carefully and answer the best, the one that seems best to you. There. Always read carefully. "15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Good? You guys want us? Go ahead and show them this. We have a little distribution of answers here. And actually, there's no majority vote. Plurality is C. Go ahead back to the display. But A is correct. And B. And actually, C is also correct. So if you voted for A, B, or C, ching. So let's see. We got 42 plus 22. We got 86% in those 3 bins. So you're thinking good. And go ahead and make a note. This is why it's both. The repulsion, you know, the negative Coulomb is over here on the right. It's out of the picture, okay? So it's going to repel the blue end of the water molecule, all right? The V end of the water molecule, all right? But that end is further away, so it's going to have some repulsion, but it's not going to be as strong. Because the closer, the stronger. The further away, the weaker, just like with gravity. And the red side of the water molecule, the positive side, the hydrogen end of the molecule, is a little bit closer to the Coulomb's over here to the right. It's rotated, so now your positives are there on the right side, and they're going to get a attraction to the negative Coulomb, and plus so that's good, plus they're a little bit closer, a little bit stronger, right? So the net pull is to the right. So make a note of that. It's a combination of A and B, and that means C is the best answer for that one. All right. Now, let's talk about interactions. Right? The charges in electrons, they're intrinsic. They are in a proton as well. We can't find any protons in nature that are just kind of floating around with anything smaller than 1.602 times 10 to the minus 19 coulombs. Same with electrons. They seem to be the smallest negative charge. Everything is built from that. They interact in the following way with the electrical force, the electromagnetic interaction, or what we call the Coulomb interaction. And that's basically that like charges repel, unlike charges attract. And also, in matter itself, we know that ions can form, all right? And I kind of already mentioned it a little bit. If you have a regular neutral atom, like this picture here, is the pink picture on top is an element with 3 protons in the nucleus, 3 pluses, and 3 minuses in orbit, okay? And that's lithium, Lithium, lithium. Neutral lithium is going to have 3 and 3. Neutral. And atoms like to be neutral, right? And so they like to have +3 and -3 if they're lithiums. Now, if you kick out an electron, if you boot that outer electron, you now have a net positive. Okay, so the lithium ion is a positive ion. Oh, did I say lithium ion? Yeah, so if you have a lithium ion battery, these are the things that you're working with. All right? And that electron is important. That electron that gets booted, yeah, it's important. Now, it's possible to get a negative ion. All right? Here's a way, down here in pink, in light pink, down here at the bottom now. All right, that's a neutral lithium. Now, if you jam in, you crash in there and smush in there an extra electron, you can do that. It'll be attracted to the positive nucleus, and so it'll be bound. But the net charge of that atom is going to be negatory. So you have a negative ion. All right. Now, if you have a positive and a negative next to each other, 2 ions, guess what happens? They bond together. A positive ion and a negative ion, they're going to tend to bond together. And that kind of a bond, if it's between 2 different elements, it's called an ionic bond. The simplest ionic bond in everyday use is table salt, NaCl, sodium chloride. That's an ionic compound formed by an ionic bond, a sodium positive and a chlorine negative. The chlorine steals an electron from the sodium, and then they say, all right, I've stolen, but now we're going to bond together, right? So it's kind of like your little brother stealing something from you. He's still in the house. He's still part of the family. And when that happens, they bond together, right? Because you don't want to let your little brother get away with something, okay? So you got to keep it close. Keep an eye on that little joker, all right? Raise your hand if you have a little brother. All right, so if you have a little brother, you know what it's like. I got a little brother. I got a big brother. I got 2 big sisters. I got 1 little sister. I got a bunch of each. All right, mental IQ test question. All right, now that I got you thinking about atoms and nuclei and stuff like that, electrons, let me ask you this. Questione number 3. Clicker question, mental IQ test. Please answer A, B, C, or D. What keeps the nucleus together? Now, this is a helium nucleus. By the way, I mentioned alpha particles a short while ago. Another name for alpha particle is the helium nucleus. The helium nuclei is the alpha particle. So beta rays are electrons. Alpha rays are actually helium nuclei. And then X-rays are X-rays. photons. What keeps the nucleus together? 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, go ahead and display this. We got a little mixture here of A's, B's, C's, and D's. Go back to the regular display. And actually, this is the correct answer. There is a third force. So for those, and you know what? Only 26% of you voted for that. If you're one of the, raise your hand if you're one of the 26%. Good. If you voted for that, you were thinking like a scientist, because this is how we figured out that there is a third nuclear force. So make a side note. There is a third force of nature. Gravitation we got. Electromagnetic interaction we got. But when they figured out that the nucleus was positive, they realized, whoa, there's another force even stronger than electromagnetic repulsion. Gravity's really weak. But there's a third force. It's called the strong nuclear force. And there's a fourth force called the weak nuclear forces. There's two nuclear forces. One of them is strong, one of them is weak. This is the strong. So if you voted for that, good thinking. You're thinking like a scientist. All right, now, let's talk about electrical conductors and insulators for just a few minutes. All right. You know, what makes a conductor? Well, a conductor is a material where the electrons are free to move throughout the material, or relatively free. Okay, so for instance, lithium, that outer electron, that third electron out, is going to be relatively, it's further out, so it's going to be easier to strip off because it's further away. It's going to be relatively easy to move about. So if you have a big chunk of lithium, that electron, out of all the lithium electrons, is going to tend to move fairly well, and that's a conduction electron. Okay? If you add charge to a piece of metal by contact, those extra charges will tend to move easily, and they'll set up shop where they're as far away from each other as they can manage, right? By repulsion. Okay, so they're going to tend to dissipate. So if you put them in at point A, they're rapidly, in a very rapid manner, going to move away from point A as far away. They're going to try to distribute themselves equilaterally around the surface of the object. So examples of conductors are things like metals, graphite, in other words, carbon. That's pretty good at conductor. And ionic solutions. And we were just talking about ions. Here's a picture of an ionic solution. Well, you can't really see the solution, but the juice inside the lemon, yeah. It's acidic, and that means it's got ions. So if you put two different kinds of metal, like a little piece of copper wire, you poke that into a lemon, and a little steel paper clip, and then connect it to a wire, the current will flow. Not a whole lot, but it will. I mean, and when they first figured this out, back in the 1700s, Galvani in Italy, he realized that the contact of two pieces of different kinds of metal would cause current to flow. So two different metals and then an ionic solution. And what happens is the current will flow, and then this particular design, if you sketch this, you could do this as a demonstration or a science fair project. I mean, if you're an elementary ed teacher or secondary ed, you could do this till the cows come home. It's very easy to do. Just get a little tiny compass, any compass, and then loop your wire around it like that, and that becomes an electromagnet. as soon as current starts to flow. And that'll change the direction of the compass needle. So you can connect it and disconnect it, and you'll get the compass needle to move. And when it moves, that means you've got current. Side note, potatoes also work. Side note, grapefruit also works. Side note, oranges also work. Side note, I don't know about mangoes or papayas, but probably. Electrical insulators. These are materials in which the electron motion is a little bit restricted. So if you add charge to an insulator, like a piece of plastic, it'll tend to stay there. Right? It won't try to move away. So examples are glass, wood, and diamond. Diamond's considered an insulator. The electrons don't move very good. And then in between these two substances are things called semiconductors, which is what they make in all computer chips out of, silicon and stuff. They conduct or they insulate depending on the voltage circumstances. So if you apply a voltage, you'll get one behavior. If you take the voltage off, you'll get a different behavior. It'll act like an insulator. All right, now I want you to write down this name, Coulomb. There's a picture of Charles Coulomb. He's a French guy, born down in Martinique. And what we're going to do on Tuesday next week is talk about Coulomb's work. He's the one that did for the electromagnetic interaction what Sir Isaac Newton did for gravitational interaction. Okay, there'll be some homework tonight, or maybe tomorrow morning. You're dismissed, 11:49. I'll see you next week. Marion.